The squeeze theorem basically says if I have one function and another function, right? So clearly f and h here, one's above the other, right? And then a third function that's bounded between them, right? So if f of x is greater than or equal to g of x, which is greater than or equal to h of x for all x, then the limit is what do I want to say here? Yeah, sorry. And if the limit as x goes to c of f of x equals the limit as x goes to c of h of x, then what do you think? Right, so you can see that f is squeezing down to 0, h is squeezing up to 0. What's happening with that middle function? It also has to go to 0, right? Squeeze function, yeah? The hard part about this is finding those squeezing functions. That's the hard part, is finding the squeezing functions. And so, but that's the piece I'm not going to ask you to do, right? The hard part about the epsilon delta proofs is finding delta. I'm not going to ask you to do that. The hard part about the squeeze function is finding the squeezing functions. That's the tricky part. So just to give you an example, if I have the function x squared times 1 over sine x, sorry, sine of 1 over x. Now we know sine of 1 over x, that limit at 0 doesn't exist, right? It oscillates, right? You remember seeing that function, the oscillator? But in this particular case, yeah, question? Yes. Yeah. So I'm saying, right, I've got an upper function, a lower function, and a middle function. And the upper and lower go to squeeze down to a single point. Then the middle one's got to squeeze down to the same point. Nice. So in particular, we'll look at x squared sine of 1 over x. Right? So if I don't know what something looks like, I want to put it on the calculator. Even if I do, I probably want to put it on the graph. I want to look at it, right? So y equals x squared times sine of 1 over, times sine of 1 over x. Right? So what we're going to do is look at a particular squeezer. What do you think squeezes this thing? I don't like how this turned out, so I'm going to get rid of this. Get rid of this. There, I want that. So the squeezer above, it should be obvious is y equals x squared. Not easy to find it, but how can you tell? What do you know about sine that would tell you that the squeezer is just the x squared, not the x squared times sine of 1 over x? Sine is at most what? What's the highest value of sine? 1. So now this x squared sine of 1 over x at the most is just x squared times 1. Right? Yes, you with me? And what's the bottom squeezer? What's the squeezer from below? What's that? It's well, no, negative x squared. Nice, nice. Woohoo! Look at that. Crazy, right? What's happening at 0, 0? What's happening at 0, 0? Except for that's right, that red function doesn't exist at 0, right? Because I have the sine of 1 over x, the sine of 1 over 0. What the hell is that, right? But the important thing is to remember when I'm doing a limit, do I care about getting all the way to c? No, I just want to be able to predict what height I would be at if I was on that red curve going towards 0, right? From either direction. So there's a squeeze theorem, right? We know that x squared is greater than or equal to x squared sine of 1 over x, which is greater than or equal to negative x squared, because sine is at most 1 and at least negative 1, right? Right? And we know that the limit of plus or minus x squared as x goes to 0 is 0, correct? Yep. So, conclusion, the limit as x goes to 0 of x squared sine of 1 over x is also equal to 0. I don't care about getting to 0. I'm just asking you, if I'm on that red curve, where am I headed to? What height am I headed to as I go to 0, 0, right? So I'm not going to ask you to, hey, show me this limit by finding the functions that squeeze onto this other function. What I'm going to do is I'm going to show you the most famous version of the squeeze theorem, and then we're going to do limits with the result. So we're going to memorize the result from this next squeeze theorem, and we're going to do limits based on the result. Okay? So the theorem is basically this. The limit as x goes to 0 of sine of x over x is equal to 1. This is going to be memorized, and then we're going to do variations on it and find limits on variations of this particular function. Now, we saw this one already. We looked at this one already. If you remember, I had, right, if we think about the sine function, right, at 0, sorry, you remember I had drawn that tangent line and we could see that the slope was 1. You kind of remember that? We did it, I think, Monday. But I certainly can think of the point 0, 0 and the arbitrary point x sine of x. And I can get a slope there of sine of x minus 0 over x minus 0, which you see becomes sine of x over x. So there's really a slope here, right? You kind of remember seeing that Monday? But I want to use a squeeze to show that this thing is true, okay? So I want to look at 3 different functions on Desmos. Oh, shoot. Forgot to record, did I? Am I recording? Oh, no, I am recording. Nice. So I want to look at 3 different functions. I want to look at tangent of x. Nope, y equals tangent of x, sorry. What the hell's going on? Something's not right. Let's see, y equals sine x. There we go. Y equals cos x. Nope. Yeah, y equals x, and y equals tangent of x. Do you see a squeeze happening? At 0, do you see a squeeze happening at 0? Yeah. Now it's pretty silly, right? Tangent is the green one. That's if we're looking at the right-hand side, right? Tangent is the green one. Sine is the red one, and it's squeezing on y equals x. Not that y equals x is a difficult function to deal with for a limit, right? And on the other side, they're switched, right? But no big deal, right? Because when I'm dealing with negatives, what happens to my signs of my inequalities, they switch. So I can actually talk about this squeeze that the tangent of x is greater than or equal to x, which is greater than or equal to sine of x. Yep, you with me? But that's not what I want, right? Look at what I want. I want sine of x over x, right? So I want to make that happen with this squeeze, right? So what do you think I can do? I'd like to squeeze on this particular function, yes? I would like this to be here, not the function x. I'd like sine of x over x to be there. What do you want to do? Multiply by sine? Almost. Not multiply. Divide by sine. So I get tan of x over sine of x is greater than or equal to x over sine of x is greater than or equal to sine of x over sine of x. Okay, what happens? Nice. So the right-hand side is 1. Left-hand side? 1 over cosine. Right? Because the sine is upstairs. That gets canceled with the sine downstairs. So I'm left with that cosine downstairs. Right? Everyone agree? Hello? Now, but it's still not what I want. I want I don't want x over sine x. I want sine x over x. So what should I do? Hmm? It's okay to be wrong. Nothing wrong with being wrong. We flip them. Nice. I get cos of x is less than or equal to sine x over x, which is less than or equal to 1. Right? When you do reciprocals, your arrows change, right? Yeah. So now I want to squeeze on the outside functions, right? So we know the limit of as x goes to 0 of cos of x is cos of 0 is 1, right? We know the limit as x goes to 0 of 1 is 1. What's the height of 1? The height of 1 is 1, right? So all of this tells us that the limit as x goes to 0 of sine of x over x must also be 1. Memorized, okay? Memorized on the formula sheet or the tattoo, your choice. So here we go. And so first of all, before I do some problems, I've got problems for you. They're not in the book. They're in our chapter 2 review. So past exams and etc. Chapter 2. Where the heck is it? Oh, there it is. Chapter 2 review. Right? I had said yesterday that you could do problems 1, you could do problem 2, you could do problem 3, and now we're on problem 4, right? And I got a mistake here. No. Notice I got in number 5. I've got you showing the squeeze there that I just showed, right? But you don't really have to do that because we just did it. But I've got 3 squeeze problems here for you to do. Yes? Now, I need something else first before I do one of these. Okay? If the limit as x goes to c of a times f of x, of f of x equals L, then the limit as x goes to c of a times f of x equals a times the limit as x goes to c of f of x equals a times L. What the hell am I saying here? What the hell am I saying? What's a nice little shortcut way of saying this? And the hint is here. And of course, a is just a real number, right? Just a number like 3, yes? Or pi. So what am I saying here? A is just a number, right? Where is A in my bottom line here in the conclusion? Then, where is A first? Yeah, in terms of the limit, where is A in terms of the limit? It's inside. Yeah, it's inside. Right. It's part of the limit. It's inside the limit. And the second place it is outside the limit. So what I'm saying here is I can move a constant in or out of a limit anytime I want. Coefficients move in or out of limits. I can move that number in or out of a limit. Of course, because the limit is dependent upon what? What's in control here of this limit? Say it again. X. That's what you said, right? X? Yeah. X is in control, right? I'm moving the X closer and closer to C to find out what's happening to my function, right? So all A is doing is moving my function up, right? Multiplying by some number will move it up or move it down or whatever, right? So I don't write this part. I'm going to do a little epsilon delta stuff here, okay? Don't write it, okay? What's this first thing tell me? It tells me that for every epsilon greater than 0, I know a delta. We know the delta such that 0 is less than the absolute value of x minus c is less than delta implies the absolute value of f of x minus L is less than epsilon. I know that delta. I found it, right? Because the limit exists, so we know there's a delta, right? You with me? And what does that delta do? It keeps all of the function on the dartboard. All of the function between that radius of delta will stay on the dartboard, so I can squeeze it down and get the limit, right? Okay, so what's happening when I do this next one? I want to look at, for every epsilon greater than 0, I should be able to find a delta greater than 0. I don't know if I have it yet. Such that in my second limit, look at it. 0 is less than the absolute value of x minus c is less than delta implies what? Though what's changing? What's my new function? It's not f of x was here, right? F of x was here, but now I'm in this one. So what's changing? Instead of f of x, I have what? I have a f of x. And instead of L, I have AL, right? But look at what happens to that. What can I do with that A? I can factor it out, right? Now, if it's positive, no worries, right? No worries, right? If it's so, there's 3 cases I have to worry about. But notice what I'm actually showing here, right? That f of x minus L is less than epsilon over A. 3 cases of A. Positive, 0, or negative, right? Positive, done. No problem, the same delta works. Negative A, it's going to just switch. I'm still going to factor out the positive, but the negative left over will switch these two. Do you care about me switching these two? No, because of the absolute value, right? And then if A is 0, what happens originally? What happens here when A is 0? This is gone. This is gone. Is epsilon bigger than 0? Automatically. So what delta is working? Right? The same delta that worked for f of x works for a times f of x. Better yet is if I just see f of x, right? And then I see a times f of x. Right? Again, think of a as a positive number bigger than 1. What's it going to do to the function? This. So what's it going to do to the height? That. Right? This is easy, right? This is easy to see, right? That my height here is L, and my height here is a times L, right? But that's the proof. I knew the delta if I had the limit, and then if I have a times the function, it's just a times. The same delta works. Okay, back to the squeeze. Here we go. Let's find the limit as x goes to 0 of sine of 2x over x. By the way, do that limit numerically. Do that limit numerically on your own, right? The original one, right? What was it? The limit as x goes to 0 of sine of x over x is 1, right? Do that limit numerically on your own. Verify for yourself that you'll agree with that. We did it graphically, right? We did it graphically. Maybe I should show you again graphically. Nope. O comma O. 0. Oops. 0 comma 0. Oops. Come on, Robert. So remember, sine of a over a is y2 minus 0 over x minus 0, right? Yeah, remember I just said that before? Don't let me just, where did I do it? Yeah, here, right? Sine of x minus 0 over x minus 0 is sine of x over x, right? So what I'm doing is I'm going to create that secant line, yeah? So y minus sine of a equals sine of a all divided by a times x. Missed it by that much. Oh, x minus a. Nice. And sine of a over a is my slope. Right? You with me? Everybody with me? I'm worried that I'm confusing anyone. Everybody okay? Yeah, it's the slope. Yeah, it's the slope of the secant line with the fixed point 0, 0. Yeah, Yeah, nice. So watch what happens to my slope as I move, as a goes to 0. What's happening to my slope? Oh, am I calculating my slope? Oh, there it is down here. Sorry. So there's my secant slope. Where is it going to? 1. And remember how I showed you on that Monday that you can really see that the right base of 1, height of 1. So back to our problem now. So the way I'll write this problem, I'll say, hey, knowing this limit, right, find the above limit. Right? So there's the wording. I know that the limit of sine of x over x is equal to 1 as x goes to 0. But what happens to sine of 2x over x as x goes to 0? Right? You with me? So we're going to do this a couple of ways. The first way is using a trig identity. So what trig identity do you know here? This is when the pre-cal knowledge starts to hurt a little bit. If you take a look at our textbook, the very next page, sorry, the first blue page, where the hell is it? Uh-oh, maybe it's the other way. Oh, there it is. When you first open the book, there's if you bought the physical book, there's a cardboard instead of just like paper, a thick piece of paper that has everything on it that you should have memorized from pre-cal. I would suggest putting it on your formula sheet. So it's 2 pages of everything you should know, have memorized from pre-calculus. Do you remember how pre-calculus was? What was tough about it? Lot of material, right? What else? Nothing else was tough about it? Just a lot of material, right? It's never ending, right? I thought it was also eclectic. It seemed like we had topic after topic after topic that was like everything's different. All of a sudden, brand new course. All of a sudden, trees. All of a sudden, inverse trees. Everything is different. For me, that's what I think. And I put Calc 2 as the most difficult, pre-Calc is the second most difficult. Calculus is pretty easy. Why? Calculus is to flow from one thing to the next without being real eclectic, and it's not that much material. If you think about it, how many things have we done so far? 1. Limits and derivatives are the same thing. Right? So, by the time you get to Calc 2, the back of the book has 6 pages of everything you should have memorized from Calc 1. Okay? My goal is to have you ready for any Calculus 2 teacher at any school. Okay, so when it starts getting real tough and there's more and more to do, just know I'm trying to get you ready for Calc 2 with any teacher at any school. Trig identity here, who's got it? What's my trig identity here? Nobody? What is it? Nope. It's 2 sine x cos x. What can I do with the 2, you think? I just proved it to you. You can do something with that 2. You can move it outside the limit. This a limit, I'm going to secretly apply it to pieces of the function as I wish. So I'm going to do 2 times the limit of that first piece, and then get the limit of the second piece. And I have to be careful how I choose my pieces, right? If I choose the limit of sine x only, what will I get? I'll get a 0, right? So, but if I pick the piece of sine x over x, what limit do I get for that piece? 1, because that's the piece we have memorized. And what do I get for cos x? I get cos of 0, right? Cos of 0 is 1. So I get a limit of 2. This is the mistake I see all the time. Does sine 2x equal 2 sine x? Can I just take that 2 out like that? You know how many times I see students writing this? Oh, I can just take the 2 out of there. No, you can't. You don't even know what's in there. It's a function, right? Sine of 2x. I don't know what's inside the machine. Sine is the machine. It's a Coke machine. Are these the same? Say no. Good. This one is what kind of modulation? This is what kind of modulation? This is your pre-calc stuff you're supposed to have memorized, damn it. I know 2 sine x equals 2 sine cosine. Well, no, 2 sine x sine cosine. Yeah. This is called frequency modulation, like FM radio. This is called amplitude modulation. Sine x is at most 1, so now it's at most 2. Right? Frequency modulation says it's going to repeat the sine twice. It's going to repeat the wave twice. 2 times sine says it's going to make the wave twice as high. All right, we had so please don't ever do this, please. If you do it, I'll scream and cry and make marks on your red marks all over the paper, like whatever that crazy guy did. Let's do this a different way with something I call a theta substitution. Say again. The theta substitution. So meaning I'm going to let theta equal 2x. So what does x equal? Nice. As x goes to 0, where does theta go? Yep. So now the limit as theta goes to 0 of sine of theta over 2, what can I do with that 2? Yep. So 2 times the limit as theta goes to 0 of sine of theta over theta. Well, that's just like sine of x over x, right? So where does that limit go? To 1. Say what? Yep. 2 different ways, because on your test or on your quiz, I'll say solve this using a trig identity or just solve it. And if I say solve it, do it any way you want. We'll try another question. Yeah, as x goes to 0, right? As x goes to 0, look at what, can you see that 2 times x is still going to 0, so theta is going to 0. Right? It's getting there faster. But who cares? So knowing the limit as x goes to 0 of sine of x over x equals 1, find the limit as x goes to 0 of sine of 3x over 2x using a trig identity. Oh, how do you spell identity? How do you spell identity? Is there what? Yeah, thank you. I'm just losing my mind for a second. Identity. Identity, yes. Thank you. Well, first of all, you should see that the 1/2 comes out, right? Yeah, you agree? Right? The coefficients can move in or out of a limit, no problem. Right? Just thinking about multiplying a function by a constant, just going to change the height of the function, right? But I need an identity for sine 3x. And the one I want is what? Sine of alpha plus beta is sine alpha cos beta don't tell me. Yeah, plus cos alpha sine beta. You remember that one from pre-cal? Just lie to me, please. You remember that one? Yeah, good. So I'm going to do 1/2 times the limit as x goes to 0 of sine of 2x plus x all over x. And so my alpha is 2x, my beta is x, right? So sine 2x cos of x plus cos of 2x sine of x, all divided by x. So we do something called divide and conquer. When I have a multi-term numerator, I can split it up into, right, a couple of multi-fractions, right? So we're going to do sine 2x cos of x over x plus cos of 2x sine of x over x. What's that? You just don't know the identity, right? It's on page 2. Page 2. On the right bottom right hand side. Nope. Sine of Sine of x plus y. I use alpha, beta. Sine alpha cos beta plus cos alpha sine beta. So sine 2x cos of x plus cos 2x sine of x. Right here. Okay? Then I split it into two pieces. Divide and conquer. We'll do that a lot this semester. When you see a multi-term numerator, you just split it. Right? You can clearly see that now. If I add these together, I get a single denominator of x, right? Okay. But this thing is saying, hey, what's the height of this? And what's the height of this? And then tell me the height total, right? So I can apply that limit to each of those pieces. So I get 1/2, the limit is x goes to 0 of sine 2x cos of x all over x, plus the limit as x goes to 0 of cos 2x sine x over x. And then you can see what I'm going to do. I got to change this guy, right, to what? 2 sine x cos x. Remember how I said some problems could take a couple of pages? Don't fight it. Don't squeeze it. Don't start writing sideways on the paper. Use paper. Take paper from the school. Right? Take your time. Be patient. I'm going to split each of these limits into a couple of pieces. I'm going to do 2 times the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of cos squared x, right? Cos times cos, plus the limit as x goes to 0 of cos of 2x times the limit as x goes to 0 of sine x over x. You can see I've applied the limit to pieces that I know will work. I know this limit, 1. I know this limit, it's cos squared of 0, that's 1. I know this limit, it's cos of 2 times 0, that's cos of 0, that's 1. I know this limit, it's 1. I've changed my sine 2x in green to 2 sine x cos x again. And then the other cos x is still there. What do I get, 3? Yeah. No, you can't take 3 out. You can't take that 3 out. This 3 cannot come out. What is this 3 saying in the original? What is that 3 saying in the original? That's a 3x, right? Sine 3x, yes? What is it saying? It's saying repeat the cosine 3 times. Right? So go around the circle 3 times as fast. If the 3 was outside, what does it say? Make the sine 3 times as high. Not the same thing. You cannot take that 3 out. All right, let's take a quiz. Nice. Yes, sorry. Is that okay there? Exactly. So when you see cos squared of x, that means find cos of x and then multiply it by itself, right? Well, sorry, I ran a little bit over today, but got 20 minutes for the quiz. Cos of 2 times 0 is cos of 0. 1. Cos of 2x, as x goes to 0, becomes cos of 2 times 0, which is cos of 0. On both sides, well, they use decimals, they use quarters, they use your calculator, nothing else. I know that was a lot to think of, but just like rewrite it, make sure you can justify.